Let's talk about ionic compounds. First, you have to know how to determine if an element's ionic, because there's different rules for naming and writing and how we treat ionic compounds and covalent compounds. An ionic compound is always going to have a metal and a nonmetal, or a polyatomic ion and metal or nonmetal. It's easy to determine if it has a polyatomic ion because the formula will have more than two different types of elements, or it'll have a name off of the polyatomic ion handout. It's important that you go back and download that handout and keep it on hand while we're doing this naming, because I expect you to be able to know the names of those polyatomic ions. But for the rest of the elements, you should be able to look at the periodic table and tell if they're a metal or a nonmetal. Look at this example here. Do you see this line? We call this the stair-step line because it looks like stairs. And it divides our metals and nonmetals. Now, if the element's touching that line, they're generally a metalloid or a semiconductor, and I won't put those in a formula without talking to you. One exception to this is aluminum. Aluminum touches that line but is still a metal. So everything above and to the right of this line over here is a nonmetal, with one exception, hydrogen. Hydrogen is over here because it has one valence electrons like everything else in that group, but it is a nonmetal. Everything else on this periodic table is a metal. So you can see we have mostly metals, so I should be able to give you an element and you can look at a periodic table and tell if it's metal or nonmetal. I know some periodic tables don't have that stair-step line, but you can see the general idea of where they would be. And let's talk about the rules for how we name a compound that's ionic. And that we just discussed they could have three different elements. They can have a metal, nonmetal, and they can have polyatomic ions. So if one of the parts is a metal, that name doesn't change. So if it's aluminum, you just write aluminum. If one of the parts is a nonmetal, you change the ending of the name to IDE. Now, be aware that I said change the ending, so we don't just tack it on. It doesn't become oxygenide, it becomes oxide. And it can be a little confusing about where to make that cut for the IDE, but there's only about 10 nonmetals that we'll use, so you'll figure it out, and you've actually heard these terms, like fluoride is the ion version of fluorine, chloride of chlorine. So you've heard a lot of these terms even before you took this class, just in your everyday life. And if one of the elements of your compound is a polyatomic ion, you don't change that name either. So the only thing you're changing is nonmetals. Remember that all compounds have two-word names. So if you've come up with more than two words, you're doing something wrong and you need to go back and check. It usually means you have a polyatomic ion that you didn't name properly. So let's practice naming. It might be helpful if you pause the video while we're doing some of these examples and see if you can name them yourself in your head before you hear me talk about the answer. If we look at this first one, we can see that Mg is a metal, so its name doesn't change. It's magnesium. We should also be able to look at the periodic table and see that Cl is a nonmetal, and it's chlorine, but we have to change the ending to IDE. So it becomes chloride. So the name of this compound is magnesium chloride. I do want to make one important comment here. Depending on the font, that lowercase l can look exactly like an uppercase I. You will never have carbon and iodine together. So if you see this, assume it's Cl, not Ci. So the name for this compound is magnesium chloride. So let's look at the next example. When we look at it, we can see we have three different types of elements. And that means we have to have a polyatomic ion. So take a look at your polyatomic ion handout and see which part of this is a polyatomic ion. You should see that OH is the polyatomic ion hydroxide. and we don't change the name. So the second word of our compound is just going to be hydroxide. And the first word is going to be potassium because K is a metal and we don't change metal names. So we have potassium, hydroxide. And I apologize for the terrible writing. The PowerPoint does not accept the tablet writing as easily as some functions. So look at the next one. And again, you have 3 different types of elements, so you know you have a polyatomic ion. And this particular polyatomic ion is a little bit special. It is the only polyatomic ion we have that's positive. So it's the only one we'll see at the beginning, replacing a metal. And it's NH4. Its name is ammonium. Be very careful. Ammonium and ammonia are different compounds. So be really careful when you write and say this name. Ammonium. And the F, fluorine, turns into fluoride. Look at our next example. Be is a metal, and it's beryllium. And N is a nonmetal, it's nitrogen. So the name of that compound is beryllium nitride, because we changed the ending of the nitrogen to IDE. Let's look at this last example. Even though there's parentheses, the naming rules aren't any different. The parentheses just tell us that there's a polyatomic ion. You won't see parentheses unless there's a polyatomic ion. So Ba. Hush, you gotta take that somewhere else, okay? I don't care if you chew on it. You just can't chew on it right behind my microphone. Okay. So Ba is a metal, and it's barium. And we don't change the metal, so the first word of this name is barium. And PO4 is phosphate. Be really careful because there's also phosphite. And if it was just plain potassium, it would become phosphide. So those are 3 names that are really close. Be really careful about which one you're writing. So this name is barium phosphate. Let's talk about the rules for how we write the formula for an ionic compound. When you're dealing with an ionic compound, there's only one way that 2 ions can go together, because the charge has to be balanced. There has to be the same amount as positive as negative, because a compound has to be electrically neutral. That means all the atoms have their full outer shells. Unlike covalent compounds that can change, like carbon monoxide is CO, but carbon dioxide is CO2, because there's lots of different ways they can go together. So we could think through if I have this many positive, how many negative do I have to have, and balance the charge. Or we can do this trick that we call dropping and swapping. That's where you write the ions with the cation first, you drop the positive and negative sign, and swap the numbers. I'll show you an example in just a minute, and it will make a little more sense. When you're done, you have to remember to reduce the subscripts to the lowest whole number ratio. So if you have 2 and 4, divide them both by 2 to get 1 and 2. And you have to put parentheses around polyatomic ions if they get a subscript, because you have to protect that polyatomic ion. Remember, you're saying you have 2 of the whole polyatomic ion, not just 2 of the last element in it. So before we do some examples, we have to talk about how we know the charge of an element on the periodic table, because that was the very first step, is write the ion. And you should know this because you know the number of valence electrons. When you drew your Bohr models, you saw that all group had the same number of valence electrons. And this is part of the periodic table. I took out the middle section that would usually be like right here. So these are the only ones we're going to really use for naming in this class. And you know that group 1 has 1 valence electron. And atoms bond in order to get a full outer shell. So in terms of valence electrons, that means that the shell that we're starting in here will either go up to 8, or we'll get rid of everything in that shell and have 0, meaning the shell underneath is full. So group 1 has 1 valence electron. They're not going to gain 7 electrons. They're just going to lose that 1 valence electron. And if they lose 1 negative charge, instead of being balanced, now they have a charge of +1. So all the elements in group 1 have a charge of +1. In group 2, they have 2 valence electrons. They're not going to gain 6. Instead, they will lose those 2 and have a charge of +2. So everybody in group 2 has +2. So we skip over this whole section here, and we get over here to group 13. And group 13 has 3 valence electrons. And instead of gaining 5 to get to 8, they'll lose those 3 and have a +3 charge. So all the elements in group 13 have an ion of +3. Now, group 14 is a little tricky because they have 4 valence electrons. And this means that they can gain 4 or they can lose 4. I won't ask you for any examples out of this group on the periodic table, not until you get to chemistry at least. But if you look at it, you can see a lot of these are metalloids and semiconductors, so they can be either a metal or nonmetal, either gaining or losing. So group 14 is a little fuzzy. But group 15, at least all the ones we'll use in group 15, because they have 5 valence electrons, they will gain 3 negative charges and have a charge of -3. Group 16, because they have 6 valence electrons, they'll gain 2 and become -2. Group 17 will gain 1 and become -1. And if you look at our group 18, those are noble gases. They already have 8, and they're not going to make ions. You know that they're called inert, which means they don't react with other substances. So you might keep this in your mind, sketch this little graph, help you remember the charges of your ions, because you'll have to know that when you're naming. Let's do some practice. You see that I've written names here, so you have to know which name matches with which symbol. You'll get used to the more common ones, but you might keep a periodic table with names on it handy for this. So look at this example. We have lithium. We have lithium sulfide, and the first step for dropping and swapping is to write the ions with the cation first. That means your positives should always be first. If it's written like an actual name, the cation will always be written first already. But let's look at our lithium. Lithium is in group 1. So if we look at our periodic table, we know that lithium has a +1 charge. So we're going to write our ions with our charges included, because otherwise it's not an ion, +1. And we know the 1 can be understood, but for right now let's show it. Let's talk about sulfur, because we know sulfide was sulfur before we changed the name. Sulfur is in group 16, so it has a -2 charge. So that's the first step of dropping and swapping. The second step is to drop positive and negatives, so we're going to ignore them from now on, and swap the numbers. That means this 1 comes down here and becomes a subscript for the sulfur, and this 2 becomes a subscript for the lithium. And we get Li2S1. And remember, you don't write the 1, it's understood. So Li2S1, that's lithium sulfide. It's the only way lithium and sulfur can come together as ions to balance the charge. Let's do another practice example. You might want to pause the video and see if you get the same answer before I write it down. Let's look at calcium nitrate. Now, first of all, some of you might already have noticed. Remember, if it's a nonmetal, what are we going to do to the ending? We're always going to change it to IDE. So if this second word in your name does not end in IDE, then it is not on the periodic table. It is a polyatomic ion. Now there is one exception. Hydroxide does end in IDE and still is a polyatomic ion, but everything else, if it doesn't end in IDE, then it's a polyatomic ion. If it does, then you know it's an element. So let's look at calcium. Calcium is in group 2, so the ion is Ca plus 2. And now you have to look at your polyatomic ion sheet. And nitrate is NO3 minus 1. So we've written our ions, now we drop. We ignore the positive and negative signs now, and swap. So we end up with Ca1, which we don't write. And now something important, NO3. We know it gets a 2. We do not just change it to NO2. We need to say that we have 2 of those NO3 ions. So we have to put in parentheses and say NO3 and put the 2 outside. So calcium nitrate is CaNO3 2. Let's look at another example, magnesium sulfide. Magnesium is in group 2, so it has the ion Mg plus 2. And sulfur is in group 16, so it's S minus 2. So we drop and swap. And we get Mg2 S2. But we're not done with this one. Remember that an ionic formula has to tell you the lowest whole number ratio. And we can reduce these two subscripts. We can divide both subscripts by 2. So if we have 2 Mg's and 2 S's, we know that that's a 1-to-1 ratio. That means Mg S. For every magnesium ion, there's a sulfur ion. Let's do another example. Potassium phosphate. Look at that name. Phosphate has to be a polyatomic ion. It doesn't end in IDE. So you can look at your polyatomic ion sheet. Potassium is in group 1, so it has a charge of +1. And phosphate on your polyatomic ion sheet is PO4 minus 3. So if we drop and swap, the 1 comes here and the 3 goes there. So we have K3, and we don't need to put parentheses around PO4 because we're saying there's 1 of them. We don't need those parentheses, so we just put PO4. K3PO4. Here's another example. Ammonium sulfide. So sulfide, it ends in IDE. It's an element on the periodic table. But ammonium That is our one special polyatomic ion that goes in front. And you'll just know that name if you see ammonium. It's a polyatomic ion. So if you look at our polyatomic ion sheet, it is NH4 plus 1. And I always write the numbers for this. Sulfur is in group 16, so it's -2. When we drop and swap, the 1 goes here, and the 2 goes to the ammonium. That means we have to put the ammonium in parentheses. So we have NH4, and 2 of those, and 1 sulfur.